Next, I'm going to give the stage to Mark and Ken to have our discussion session today.
This is a very challenging discussion session because, according to the program, we have 4 minutes, and also it's Friday evening, so we promise to make this as painless as possible. So the way we have planned for this is just to simplify things, and so that you only have to push buttons to say yes or no, and we hope that this will make things easier. So please scan these, and we have prepared a set of questions. If people, so we look at the results, of course it's oversimplified. If people want to comment anything, we can do it. If people can just stay quiet and look at the results and then digest, that's also fine. And so that's it. So maybe I'll let Ken start with the first. So let's start with, everybody got the website? Yes? So let's start with a warm-up question. If you were at the dinner, so do you know from what year have the Santa Cruz Galaxy Workshop stalls been recorded? Things weren't, people, it looks like people were not very, listening. So if I'm correct, Joel, it's from 2010, and you can...
No, well, actually, the slides are there from 2010.
Okay.
The video started in 2012, I think.
Okay. So I was not wrong. I got you. Anyway, let's move to something more serious. So let's maybe
okay, so the morning session was on the black holes and AGN. Let's talk about black holes. Are all SMPH overmassive in the early universe? I think you can only select one.
Single choice, but
Single choice.
So overmassive, it means that they are they don't lie, so they lie above the local scaling relation, and so that for the mass, for the galaxy mass, they are too massive compared to the local scaling relation. Okay,
I'm actually a bit surprised that so little people voted for yes. Okay, so. So let's hear from few people who actually said no, selection effects. Somebody wants to argue about the second choice? Or who's the best observer who wants to say selection effects? Okay, Owen?
Yeah, I said no because so when you are trying to measure the black hole mass versus galaxy mass relation, there are so many things that you have to account for. Firstly, beyond the local universe, you no longer can do the dynamical mass measurements for either galaxies or black holes, and instead you rely on some so-called virial estimates that are calibrated with the reverberation mapping results, which is by itself calibrated from the local dynamical measurements of black hole mass. So you typically have at least 0.4 to 0.6 dex in the black hole mass measurement uncertainty around the intrinsic value. In addition to that, especially at higher redshifts, beyond redshift 6, I don't think people would trust, I don't think all people would trust your SED fitting results, especially with JWST galaxies. Right. So in addition to the black hole mass estimates, you also have the measurement uncertainties in galaxy mass relation. Okay, so with the, Hello? My check. Okay. So with both of these factors, you are having a puffed up scaling relation, if there's any relation left at high redshift. Okay. So beyond that, you're limited by the broad emission line width and also the AGN luminosity limit, because you cannot tell whether a broad emission line is generated by AGN or some outflows if it gets too narrow. So basically what you end up doing is that you're making a horizontal cut, selecting only the more massive black holes that can produce those broad emission lines and luminosities. And with any scatter that I just mentioned, it would just artificially give you the most overmassive objects in the high redshift universe. So I mentioned to some of the participants here that there's a paper written by Lee et al. 2024. Lee spelled as L-I. So in that work, they show that once you account for all these systematic issues, even with a local scaling relation, you can see that these JWST AGNs are actually just the tip of the iceberg of that underlying relation.
Great. There are more comments?
Another comment here?
It's a kind of follow-up question to Howard's comment. Okay, we know that there are some caveats of the observation for the JWST, and okay, let's assume that all the observed is biased to a massive one. If you reconstruct or correct this kind of bias, would you think that the population of this kind of supermassive black holes is a little bit high? The number is too high at high redshift.
I guess if I understand the question correctly, it is asking whether there is a way to correct all these systematic issues and get, like, basically moving those data points downwards to make them consistent with the local scaling relation. Is that what you're asking? Oh, so you're saying that, okay, let's suppose all those measurements are accurate and precise, then do I think these data points by themselves are overmassive? Then yes. Yes, yes. But this is the result of we're only seeing those populations just because of all the systematic issues that I just said. Yeah.
All right, maybe we should move on, otherwise we...
Okay.
I have another question. So we've been discussing a lot of, well, go ahead, Ken. We've been discussing a lot of AGN feedback and the impact this morning. So I'm asking what's needed to understand AGN feedback. Is it data? Is it other things, technical things that we need to interpret the data? Or is more simulations? What are we lacking? Or anything? All right, so the distribution seems quite clear here. Yeah, thank you. Okay, so it's probably none of the above then. We will say that this is theory. Sorry for that. I'm very observationally biased, sorry.
Anyone wants to make a comment on this question?
Otherwise, we leave it there. But it looks like, there's a big consensus that, what we're lacking from the observational side is gas,
yes.
And this will come soon.
Joel has a comment.
We have enough of stellar data.
Well, to narrow down the issues, one, I think, important question is, what is it that regulates the growth of the black hole? Is it feedback? So typically in a Bondi-Hoyle approximation, once the black hole gets to have reasonably large mass, the mass squared makes it grow very quickly, much faster than exponential. So you need something to regulate it, typically feedback. But there are other schemes, like torque-limited accretion, that don't involve feedback regulation at all. So, crucial thing is to try to figure out whether we really have the feedback by looking at nearby cases where we can look up close and see what's really going on with the black hole or not. And so I think that's a crucial piece of data that may really help to clarify.
Higher resolution data, let's say. Yeah. All right.
So we go to next?
Yeah.
Okay.
So this is from you, Ken.
Next one, agent feedback models are becoming more sophisticated, but more complicated, with more parameters. Is that the right direction to go? Nobody's voting for yes.
All right. So
Well,
we lack another question is no, because we lack of theory. I mean, data could be yes, anyway.
Well,
Right. Okay.
but
Fair.
this
Fair
question
enough.
was actually after Sophie Kodmani's talk. She talked about using self-similar solutions plus the information from GRR MHC simulations to do more complicated agent feedback models to go overcome the simple Bondi-Hoyle accretion type simulations. And models are getting more complicated, more parameters. Obviously, we can fit the data better, but is that the way we really need to go? Or is there a better way to make more progress faster?
So you're advocating for a better theory.
Better theory, yeah. Anyone wants to make comment on this?
Otherwise, we
How to make progress on agent feedback? No?
We keep going.
Okay, keep going.
So this is for Sandy. Do we have the equivalent of an HAR diagram for galaxies? Well, it looks like the answer is a bit.
Oh, this is impressive.
Yeah.
People think we're getting there.
Yeah.
The virtue of stars is that if you know two numbers, you know a lot about them. So
This is my next question.
before asking this question, a prior question would be, how many numbers do you need to know most about a galaxy?
I inverted the order, sorry. It's my next question.
Okay, so we can talk about the next
Yes,
question,
so
and then
go.
that HR diagram has to have that many dimensions.
Right.
Okay.
So this is it.
Okay. So how many key parameters are needed to describe galaxy evolutionary tracks?
So it's oversimplified. So.
It would make more sense if you said to characterize galaxies today.
Okay.
3 to 10.
This is a fair number. Now, do we know what are these 3 to 10 parameters or not? Yeah? Do you think it's okay? Do I tell the reason or? Six. Go ahead.
Hmm.
You want me to? I'm not sure I want to share that yet.
Okay. So maybe for next year.
Okay.
A comment here? Yeah.
So it's actually about the vote itself, about the poll itself. So will we be able to see the record of the voting?
Yes, I think so. I'm saving that.
Okay, great. Thanks.
All right. I'll move to the next question so that we don't stay here overnight. So I'm going to machine learning now. And I'm going to ask this question. So have we learned anything?
Have we learned anything useful from applying ML to astro data over the past 10 years?
Exactly. So this is a bit subtle.
Half and half looks like.
Yeah. So it's not clear. Really. It's really, divided, and I agree with that. Does someone with a strong no wants to say anything? Mhm. So my answer, I'm in between these two, and then so I think most of the answer depends, and it depends on what you consider something useful. If you think about a major discovery or something really new about galaxies, probably not. If you think about anything we do about galaxy evolution, most of it contains at some point some ML in any of the data processing. So many of the things that we do, for example, in massive photo Z estimation or these kind of things, has an ML component. So without it, maybe we don't have the possibility of analyzing this data. So that's why, I think it depends, but I think also there's not been a major breakthrough. If, people think about, in biology, for example, you have this protein folding example, in which it's really a major breakthrough. It hasn't happened in astronomy, I think.
Oh, sorry.
All right, so I put yes as a major ML hater. Like, of course we've learned useful things. Like, there have been hundreds of papers written with ML over the past 10 years, and like, some of them are good and some of them are like the same distributional quality that we see for other papers.
Right, I think you're right. So maybe the question is not well posed. I was, useful about galaxy formation, the physics of galaxies.
Or like, I'll grant that there's no like protein folding moment for
Right.
astronomy. I think that's a very fair reflection.
Right.
But like, I think it is clear that a lot of useful stuff, at least to me, has been done, but nothing that has totally changed the game, I think.
Right.
There's a comment.
This is kind of a similar comment, but to me, I think it's like, is it too early to ask this question? Have we ever learned something from the machine learning right now? Because the machine learning is just started.
Right.
And
Yeah.
so I think another question is that do we expect we will learn a new astrophysics by using the machine learning in the last or the next 10 years?
Maybe. But it's been, I think it indeed is moving fast, but it's been already 10 years. So it's not something that it's from yesterday. So 10 years is a reasonable time scale.
I want to ask a question related to this, which is, as you say, that there hasn't been any protein folding moment by applying machine learning to astrophysics. But is there a protein folding like question to answer in galaxy formation theory? So
that's a good point. Yeah. That maybe that's the problem, is either the data or we don't have the right questions. Yeah.
There was another, yeah, here.
Also, we have to define what are machine learning algorithms. For example, clustering. Every simulation has to use clustering algorithm to find the halos and the sub-halos.
Right.
We cannot live without them.
Yes. This is where I put the all depends thing, right?
Did you want?
I was just going to say that I actually think that this question of how many numbers are appropriate to characterize galaxy evolution is I think a potential area for getting a good AlphaFold moment. Of course, explaining it is going to take some more work, but getting the 6 numbers and figuring out what numbers they are, I think, could be one of the good areas. Maybe.
Yeah. I think Sandy has been trying these. And right.
Okay.
Anyway, okay.
Comment here.
And then we move forward.
About the question about machine learning, by the way, Joanna Wu, Simon Fraser University. I remember a talk that, Mark, you gave quite very early on, where you showed, and I was so impressed by this, where you showed that taking pictures of eyeballs in the medical field, doctors had no idea that there was a difference between male and female eyes, but the machine could tell them apart. And so I think there is a lot of potential that the machine can tell us and teach us, well, what are the distinguishing features in those eyeballs. And I think in the same way, there's a lot of potential that machines can teach us about astrophysics. We just haven't gotten there yet. I know it's already been 10 years, but I think we haven't gotten there yet, and I see potential in some other applications, which I'm happy to talk about another time.
Yeah. So, thanks. I must have a related question. There's another comment? Yeah. This is interesting.
Diane from Rutgers University. I just wanted to make a little bit of a comment about maybe the reverse, like maybe applying ML to astro data can tell us something about the limits of machine learning, because we have all this great knowledge about the statistical mechanics of astrophysical processes and stuff, which we could use as an independent metric to interpret the machine learning outcomes. So we can learn a little bit more about the actual machine itself as well. So I think it goes both ways.
Yes, and this is useful for the ML community actually, and that's a good point about Astro data, which is free and public easily and doesn't have any ethical issues. So ML people are usually happy to use this data to learn about data, but it's more for the machine learning community. All right, I'll move up. Where is my mouse? Here. I think more or less answered this question, but you can go ahead and then we'll skip it. More or less, the discussion has been oriented to that. And I think people agree that, we're still maybe at the beginning. All right. I think it's consensus, so I'll move forward. One of the things that we've been there's been a talk, I think, about interpretability. So one of the problems with machine learning is that it's a black box in many aspects, and this might be a problem for physics. So you think it's a major issue, and this is something important because for much of the ML community, they don't care about interpretability in many applications. We do care, I think, and is this, and it might depend, but.
I think it depends who you ask, because some people just care about to get the things done right. If you want to, like you did with moving from HST to Sears to do morphological classification, do you care? No. Yeah. But if you want to learn physical processes, then it's a big issue.
Yeah.
But so yeah, I think it just depends on the question.
Yeah.
Another comment over there, and then come back. Sure, okay.
Right. Mm-hmm. I agree. Yeah.
I also agree with that, and I was just going to plug also the simulation-based inference, right? Because there you have a model, you have your parameters, and the goal is to learn how those parameters affect, how to map those parameters onto a likelihood function, essentially, and how to map out that likelihood. And then everything else follows in the normal Bayesian fashion. So to me, that's a pretty exciting application. I don't think it's been explored enough in astronomy.
It's been. I think it's the next question, maybe. Let me see.
Well, there are many more comments now. three hands up now.
This is related to SBI.
I guess you're getting to this, but I think the main issue with machine learning in astronomy is our addiction to using it on simulations. Like, it needs to be used on data, because when you're using it on simulations, you're just you're getting what you put in out, and it really much more comes down to the limitations of our simulations than anything else. So please do machine learning, but do it on data.
Okay, there was one more somewhere there. Oh, I think there was one before here, right?
Right. I told it's oversimplified. So this is the whole point of this. So.
Yeah, I was just going to add on the previous question that I guess, this is sort of already stated, but that it depends on the problem that you're applying it to, and whether you're using the machine learning as a tool in like your process of doing science, or it's like the main to like help you to learn about a problem versus it's doing the learning about the problem, and depending on which of those two problems that you're doing, like it does in the first, it doesn't necessarily matter if you can understand why it's doing what it's doing. Versus in the second, if you're trying to make it learn the physics, then yes, you need to understand what it's doing.
Do you still want to make a comment? No, fine. Okay, David.
I think as we enter the world of huge amounts of data, whether from simulations or observations, the outliers are the things that often give us clues to what's really happening. To find the outliers themselves is not easy when you have, say, 50 parameters of measurements and multi-wavelengths. So I think there's no choice but to use machine learning in a sophisticated way to find the unusual objects, which then I think we've learned historically to be extremely powerful to teach us something. We just haven't got all that data, but I can't imagine that after the Rubin survey that we don't find new classes of objects and how they relate to other things in 17 dimensions, which, you know, if we could give it to a poor grad student for a PhD program, that's cruelty.
So this is more on the data exploration side, not on the SBI side, which I think. Anyway, Avishai is standing here, so I think we have to go.
Stop, I guess.
We had more questions, but I will skip them. They are there, you can answer. The final one is just this one, which I think there's only one answer. Thank you very much for the organizers again. Thank you, Avishai, and hope to see you next year.
And at this happy note, we are concluding the peak week of the workshop. I'd like to thank everybody for participating, giving talks, participating in these lively discussions, and contributing. I'd like to thank Colin again for his major organization skill. And John, of course, and we'll see you next year. Thank you very much.